Hello, everyone. Welcome to MACSMIN, Mathematics and Computer Science for Materials Innovation. This is the online part of our fourth conference, and it's a great pleasure for me to introduce Dr. Alexander Kozachinskiy from the Catholic University of Chile in Santiago. And Alexander will talk about 3 iterations of WL test, distinguished non-isometric point clouds of d-dimensional points. Over to you, Alexander.
Yeah, thank you for the introduction. So this is joint work with Valentino de la Rose, Cristobal Rojas, Pablo Barceló, and Mircea Petrache. So I want to start. So my slides are working. So this is now the next slide, right? Yeah. So I want to start with some general remarks, not with a lot of technical details, but so in machine learning, there is this problem called overfitting. The idea is that, so I don't know, let's say we have some objective functions that we want to learn, and then we get a training data. And the problem is that if our family of hypotheses or something is too large, like neural networks, so it's unless training data is very, very big, so it will perfectly fit the training data, but then when you get new examples, it will fail. And that's basically, as they say, it happens because of large VC dimension of the families that we use. So, and the general idea is that sometimes we have some symmetries in the problem, we can try to use them to fight this overfitting phenomena. So, yeah, and by the way, sorry, I forgot. So if you have any questions, please ask during the talk. That's, yeah. And so what I mean by symmetries of the problem. So well, very abstractly, we can have some set of inputs S, and then also some group G which acts on this set. And then what I say that the problem has symmetries, well, it means that we might be interested in the objective function which is invariant under the group. So if I apply an element, if I act to some input by an element of the group, the value of the objective function doesn't change. And then somehow to fight overfitting, we might need to might try to construct what they call learning architectures that are G invariant by default. So they kind of already take into account the symmetries of the problems. So that's kind of, and we make by this we make like the hypothesis class already smaller. So we need some learning architecture which basically gives the same result on objects that are like isomorphic, which means that they can be mapped to each other by an element of the group and by default. But then there is also a question, if we have such an architecture, when it's so like the first property can be called soundness, and the second property that sometimes it's useful to have, it's completeness. So if I have non-isomorphic inputs, those that cannot be mapped to each other by an element of the group, we want that in principle, at least this learning architecture can distinguish these two inputs, because if not, then not every G invariant function can be at least expressed completely. So, and there is this standard example of graph neural networks where, for example, so what is the set S can be? Let's say, I don't know, we take just graphs, like undirected simple graphs. Maybe let's fix the vertex set, and then so it will be like our data, and then it's reasonable, for example, to assume that in some problems, the objective function that we want to learn is the same for isomorphic graphs. So, and then what is this learning? And then the people proposed learning architectures that work the same way for isomorphic graphs by default. And the classical one is this message passing graph neural networks. And so the idea, well, basically they're in detail, but how it works is that initially, so if we have just a simple unlabeled graph, then we assign to every node the same initial, like what they call feature vector, and then in layers we do an update. So for an update is that what happens in this process is that for every node we look at its neighbors in the graph, and then these neighbors have these feature vectors from, let's say, in the beginning. And then what's important is that we apply update is that to determine the new feature vector of the node, we apply some permutation invariant functions of the feature vectors of the neighbors. It basically means that this function only depends on the multiset of feature vectors of the neighbors. So like multiset means, well, whether which vectors I have and with which multiplicity, so how many neighbors have this feature vector. And this ensures that, and then also for the classification, we do the same number, some number of iterations like that. And then we just look also, and then we have a set of feature vectors of all the nodes, and it also has to be permutation invariant, which basically also means that the classification should only depend on the multiset of feature vectors that you have. And then you can observe that if I have isomorphic graphs and I run this thing, this like message passing graph neural networks on them, it will give me the same multiset of feature vectors in the end, because, well, you can observe that if you have an isomorphism, since you don't, everything is permutation invariant, the graph neural network will behave the same.
Alexandra, could you clarify the concept of a graph isomorphism? Your graphs have unlabeled vertices, right?
Yeah.
No labels on vertices, no labels or orientation.
Yeah, I mean, for simplicity, so let's say we have just unlabeled nodes, so and undirected edges. So just some pairs of nodes are declared, unordered pairs of nodes are declared as edges, and some are not. And then in very isomorphic graphs means just that we have a we can map nodes of one graph bijectively to the nodes of the other graph, such that edge comes to the edge and non-edge comes to the non-edge. That's the idea, that you can permute nodes of the graph, and the result, the graphs will be the same.
Mm-hmm. Could you also clarify on this slide this chi, so with Greek letter chi notation. So initially chi 0, so this is probably the initial invariant or initial value. So you put it as empty set, right?
Yeah. So like the same. So basically, what is this chi? So the idea is that, well, the next thing that we can ask is about completeness. So if we have non-isomorphic graphs, can we at least devise, you know, this message passing graph neural networks that does different things on them? And the answer is not always. So there are non-isomorphic graphs such that such that graph neural networks will behave in the same way on them message passing graph neural networks. And the reason is that basically there exists what's called Weisfeiler Lehman test on graphs, which basically answers when for two graphs we can in principle obtain a message passing graph neural network which distinguishes them. And so what is this guy? So this Weisfeiler Lehman test, it given a graph, it produces the sequence of labels, right? So each chi0, then there will be chi1, chi2, chi3, and so on. There will be some functions on a set of that given a node output something. Well, it's hard to say what in the beginning, but it will be some iterative definition. So in the beginning, if we just have like unlabeled graph with nodes are unlabeled, the idea is that we want in the beginning just to assign the same label for every node. So, and this, for example, you can say that chi0 of v is an empty set for every v. And then in the update, we like do the maximal. What is the maximal information that we can get if we want to ensure implementation invariance, like in message passing graph neural network? The idea is that just let's assign the label after t+1 iterations of a node v to be the multiset of labels of its neighbors and labels. Yeah.
Sorry, so hang on, I'm slightly confused now, because if we start with all the vertices labeled the empty set, then on chi1 the label's just going to be the empty set, and chi2 the label's going to be the empty set, or
so okay. Well, so actually, what will be like in the after the first iteration, it will be every v will be mapped basically to the degree, to the number of neighbors. So I guess there is some confusion in this notation. So yeah, sorry. So this double brackets. They mean here the multiset. So, well, okay, the idea, so what will happen that in the beginning, so chi t of, well, if let's say t is 0, so there will be like a multiset of chi0 of u over neighbors of b, right? So, but when I write this, it basically will say that the multiset, so the elements are counted with multiplicity, so it will basically the first label of b will be, we'll say that it will be a multiset containing of k empty sets, where k is the number of neighbors, and this can be
okay. So you just, it's kind of you're counting the degree, but with empty sets.
Yeah.
Okay,
and but you're counting the degree on the next step. Yeah. So what will be chi1 on the first step, and then on the second step, well, it will be how to say it. So, for example, you look. So chi2 of v will be, you look at all the neighbors and you see what are the degrees of this, and you write them as a multiset. Just that there are that many neighbors of degree 2, that many neighbors of degree 3, and so on. So basically this will be chi2 and so there are theorems that says that, okay, and then what you can do, this is a process defined in one graph, and then if you have two graphs, you can run this process on both of them and see whether after any number of iterations, you will have the same multiset of this label. So every label will appear, yeah.
Sorry, I just want to make sure I've understood this. When you say cannot be distinguished, what are you comparing exactly? Is it just the list of all the vertices with their associated multisets at point t? Is it kind of an unordered list of vertices that,
So
where you can match up every set?
so basically it means that if I have two graphs with labels, if each node has a label, and I just look whether each label appears equally many times in one graph and in the other graph. So that's what I mean.
So you don't order the vertices or anything. You just count the number of times a unique.
That's because I want to. Yeah.
Yeah. Okay. All right. Okay. So
Yeah,
sorry.
that's because I want to.
Yeah. Okay.
That's because I want to ensure that if I have isomorphic graphs, they will have the same. In any number of iterations, they will have the same. The easiest way to say it, they will have the same multi-set of labels. So multi-set, like any label, will appear with equal multiplicities in both sets. So that and the theorem is that two graphs can be distinguished by this test if and only if they can be distinguished by some message passing graph neural net. But then it's like very easy to construct an example. So then you can ask, well, this test, can it give the same result for two non-isomorphic graphs, which we don't want. We want it to be complete, but it's easy. Where it's actually very easy to construct an example that you can just imagine like two triangles and one hexagon, because like the chi1 of every node will be 2, every node has degree 2, and then it will be just repeating over and over again. So, but then there is a big literature on this Weisfeiler Lehman test. There are like higher order Weisfeiler Lehman tests, and then people proposed, higher order graph neural networks that are equivalent to them. But of course, there is a problem that we don't know polynomial time algorithm for isomorphism problem. So it's hard here to propose a graph, some message passing graph neural networks will be complete because of this problem. Yeah, so that's
what does higher order mean? Sorry. Here, in what sense is it higher?
Well, okay, so there are like what I described here is what's known like one-dimensional WL test, and there are also k-dimensional WL tests, which, well, the main difference is that they, for example, two-dimensional WL test will have labelings of pairs of nodes. Will work with labelings of pairs of nodes. And then higher order, it means that, well, it's just that some graph neural networks, which also will, for example, assign feature vectors to pairs of nodes, and you can prove like that they have the same distinguishers power as this. So higher order, it means that there will be KWL for a larger K. So not something very deep.
Okay. Thank you.
Yes. So and then recently people. So this is kind of very standard thing now, but recently people ask the following question. Okay, but the natural, like similar problem of this kind is when we want to learn somehow this where our input is just the a finite set of points in Rd. And as I understand, the main application of all that is when D is free and we represent just molecules by this finite sets of points. I guess maybe in applications they might also have additional, not just the coordinate, but maybe some additional numbers as charge or something like that. But for simplicity, then okay, so we can have an input which is what we will say a point cloud. So the point cloud is just a finite set of points. And then initial thing is that, okay, maybe our objective function is invariant either under isometries. So here, just to specify what I mean by isometries, is just a mapping from RD to RD, which preserves distances. Or currently, it can be written as a sequence of translations, rotations, and reflections. And well, I guess the idea is that, for example, if I have I don't know anything about chemistry, but the idea, I guess, is that if I have a molecule or something, then its property may be invariant under isometries. Maybe not, it's not always true, but that's the idea. And so so we have the group of all isometries on RD acting on our finite sets of points. And so our idea is to consider to somehow give an architecture in the same spirit as this architecture for graph neural networks that are based on 1WL and higher order and KWL for larger K that I didn't define properly yet. That should, by default, act similarly on point clouds S and T, on any pair of point clouds S and T that are isometric. So it means that one can be mapped to another by an isometry. And well, the idea why we can try to use the same technique more or less is that we can represent S if we, so basically we can draw a graph of S, meaning that we have nodes are points of S, and then we just, for every pair of points, we just draw an H, and we label this H by the distance between the points. Okay, so now it will be like this, not exactly that I was what I was telling, that now we have labeled edges, but still on the next, for example, it can be shown, it's not, it requires some argument actually. So if I have two sets of points S and T, and then I just forget about the points and I just draw the graphs, this distance graph. So, and then if there is an isomorphism of these graphs, so basically if I can have map points of S to points of T that preserve distances, I can also extend it to an isometry of the whole RT. But this is more or less standard fact. So basically, to know the set rigidly, we just need to know pairwise distances.
Alexander,
Yeah.
is it in the case of labeled or indexed points?
Well, now we don't have any labels of points, but and then so isometry. So if I have two point clouds S and T, well, there is no order on them. So I just have to map somehow one into another, like in case of graphs, that pairs distances, pairwise distances are preserved. So
do you know an example of non-isometric point clouds that have the same list of pairwise distances?
The same list of pairwise distances.
So not in a matrix when points are not ordered and labeled.
You mean you just
For example, 4 points, 6 pairwise distances in, say, increasing order.
Well, I mean, I actually have an example where, for example, I have 6 points, and then for every, like 2 sets of 6 points, and every point in both sets have the same distances to other points.
This is an example from
And
Kozachinskiy, right?
yeah, there's examples like that.
Mhm.
Well, I mean, I actually can show.
Yeah, probably
No.
it will be easy. Yeah. Mhm.
This example. So yeah, so let's try to understand. So this example is actually, I guess, from Lee et al. So there are 2 point clouds here that are green points and red points. So all of them are 6, and this is how it's called, icosahedron. Yeah, and then so the claim is that so these 2 the green and the red point clouds are not isometric. Well, okay, I guess it's more or less clear, but from the picture, but still, if I look, for example, the list of distances will be the same, but like moreover, like every point will have the same distances in its own point cloud to other points. But it doesn't mean that, but there will be no isomorphism of the graph, of the distance graphs, because there will be, let's say, in one there will be a triangle consisting of the side of the icosahedron, and in the other point cloud there will be no such triangle, but the distances are the same. You can just see that if I have any point, for example, I have a green point, and there are 2 distances that are equal to the sides of the icosahedron, and then there are 2 distances. If you see that there are like these planar pentagons, for example, if I look from top to the bottom, so there is a green node on the top, and then there is a layer which is like this planar pentagon. There's another planar pentagon, and there's top-down node. So every node in both sets will have 2 distances. Okay, like this 2 distances that are sides, 2 distances that are diagonals of these planar pentagons, and 1 distance which is the distance to the opposite point of a icosahedron. Yeah. Well, I think I will have to get back to this example. So where was I? Yeah. So I wanted to define a geometric version of 1WL test. Now, if I have a point cloud S, then this geometric 1WL test also assigns it a sequence of labelings, chi0, chi1, chi2, and so on. Each chi is again a function which takes as an input a point in S and assigns it something. And in the beginning, again, every node is assigned the same value. Every point is assigned the same value, for example, like the empty set. Now, what's different is the update. The idea is that now we have like a complete graph, but they are labeled with distances. So in the update operation, let's just go. So we have some point X, and let's just go over all points in our point cloud. Remember the distance to this point Y. So we go over all Y in C, and also the label of Y from the previous iteration. And then let's just the multiset of these pairs be the new label of X. So for instance, if I have what will be after the first iteration, basically after the first iteration, chi1 of x will be the multiset of distances from x to the points of S. Multiset that if they are the same distances, we count them, we remember their multiplicities. So in our example that we saw, so there was like a multiset, the side of the icosahedron with multiplicity 2, the diagonal with multiplicity 2, and this like the distance between the opposite points with multiplicity 1, and 0 like the distance from the point itself, but it's not very useful. Again, so and then you can give this test, and then you can ask, well, if you have 2 point clouds, well, if I have 2 isometric point clouds, you can observe that after any number of iterations, these labels will be the same. Like every label will appear equally many times in both of them, because you can permute, and then everything will be the same up to this permutation. That's the idea. And then you can ask the question in which dimension, or even if there exists a dimension, this thing will be complete. So if I have any 2, so I'm interested whether the following is true. So if I have 2 non-isometric point clouds, so different in a way, that they can be distinguished after some iteration t. So they will have a different number of different multisets of labels after t iteration in this process. And so basically the whole idea why we are trying, the idea is to do that is that then we can study this question and then try to come up with graph neural networks for these specific settings, and people are doing something like that. But then when we will figure that naturally correspond to this test, and then at least we will have an understanding when we will have a complete architecture and when not. Okay, I have another example just to understand that, okay, there are like iterations that, and then after the first iteration, we get the multiset. Every point basically is assigned the multiset of distances to the other, to the points in the set. And then I just wanted to give an example how it works, and that sometimes what happens after this first iteration. So basically in this example, what I have an equilateral triangle ABC with side X, and then I also add 2 points D at distance Y from A on the same line as AB, but from the different side, and also the same for E, so it's a distance Y from C and AC. So the observation that after their labels, if I look at these 2 additional points, D and E, they will have the same label after the first iteration, because for each of them, this multiset of distances, it will include the distance between them, and then there will be a distance Y, a distance Y plus X, and this distance Z, which is the same for all D and E. So after the first iteration, these points will have the same label, but they will have a different label after the second iteration, because why is that? Because if you look at A and C, they have different labels already after the first iteration, because because A, what happens with A, let's say, it has 2 distances X to this equilateral triangle, 1 distance Y to D, and the distance X plus Y to E. But C is different, that it has 1 distance Y and the other distance is Z, if we don't look at these 2 distances as X and X. So And then we can distinguish D and E after the second iteration because D has one node at distance y, 1 point at distance y from it, which is A. And E has also 1 point at distance y, which is C, but after the second, in the second iteration, we will find out that the labels of A and C are different, and hence this will distinguish D and E because they will have only 1 point at distance y, but their labels after the first iterations will be different. And then to state our results, finally, I have to also define at least two-dimensional geometric WL test. Because I didn't do this for graphs. And then it can also be defined in some similar way for three-dimensional, four-dimensional WL test. The only thing is that notation becomes even messier, but let's try to do this at least, I guess, for 2WL. So what's the difference? As I said, that now a point cloud will be mapped to a sequence of labelings. Each now is a function on the set of pairs of points of S. So it will get 2 points on input. And now in the beginning, the initial labeling of a pair is just the distance between the points. And the update now doesn't involve distances because they are like already can be deduced from the initial. And the update works as follows. So given X and Y, now I go through all points Z in my set, and I remember the label of this Z with X and of this Z with Y. And I remember the pair of these labelings, and then I take this multiset. So, for example, after the first iteration, what we will get, if you look at it, is that we will just get for every X and Y, we will get the multiset of pairs of distances to X and Y. Basically, the idea, basically it can be seen as that we will obtain a list of triangles containing X and Y, but triangles, I mean just the distances in these triangles.
Sorry, yeah. When you say triangles, so this isn't for any pair, this is for any adjacent pair, or is it for any?
Well, it's for any pair because, well, like in the graph, all pairs are adjacent, but they have different distances.
Because it's a distance graph, so all pairs are technically, it's a complete graph. So yeah, that's fine. Okay, got it.
Yeah. And then we can do more iterations, and in the same way, we want to understand. It's easy to understand that for isometric point clouds, the multisets of labels after any number of iterations will be the same. And then the question again, when this thing is complete, in which dimension? So in which dimension we can distinguish any pair? So here are our results, which tells something about it. Sorry, can you hear me?
Yes, Alexander, but your slides are no longer visible.
Yeah, I think I lost the connection for a moment. So can you see it now?
Yes. Thank you.
Yeah. So our result says that if I look at RD and I'm asking what is the minimal KWL which is complete, we say that D-1 dimensional WL test is complete after 3 iterations, which means more specifically, we even show the following. So if you have a multiset S and then you do 3 iterations of this D-1 dimensional WAL test, and you get the multiset of labels after these 3 iterations, then from this just from this multiset of labels, you can determine your S. You can kind of reconstruct your S up to an isometry. So most probably not your original point cloud S, but some point cloud S prime, which is isometric to S. And as a consequence, this means that if I have 2 non-isometric point clouds, they cannot have the same multi-set of labels after 3 iterations, because otherwise we would reconstruct them into the same point cloud. And so we also observe that this geometric DWL test is complete just after 1 iterations in RD, but this is at the cost of having larger dimension of the test. Well, okay, first of all, in fact, we don't know whether, well, 3 iterations is our upper bound, right? Maybe just 1 is enough. We actually don't know of D-1 WL test. So what we know if we just look at specific dimensions. So for example, in R2, so if we look at this, oh, I think people didn't look too much to R2, but at least we can say that this 1WL geometric test is complete. So on the plane, you just need to have these labelings of nodes. But we only know that it's complete in 3 iterations, and 2WL is complete in 1 iteration. So in R3, what the situation is that 1WL is not complete. And basically, I already explained you why, because I had, so in this example that I show you from Lieto, well, the first, so the first one to prove it, I understand it was Peznikov and Cheryoty, but this example I think is not theirs, but from the other paper. But the point is that we have here 2 point clouds that are not isometric. Okay, this has to be proved, but it's like more or less clear from the picture. But still, if you run 1WL, it will produce the same multisets of labels after each iteration, because basically already after the first iteration, every node will get the same label, because every node in both point clouds have the same multiset of distances. And basically, after the first iteration, all of them will get the same label, and then after the second iteration, you will just have a multiset of distances to these points that have the same label. So it will be like also will be the same in both point clouds, and they cannot be distinguished. Yeah, but our result at least shows that 2WL is complete in 3 iterations in R3. So at least for R3, we know like the exact answer, which dimension is enough. But we don't know, maybe less iterations are enough. So what's open is that already at R4, what we know that 3WL is complete, but we don't know if 2WL is complete. It seems, so it's hard to actually, so for 2WL, it's harder to construct examples that full 2WL even just for graphs. Well, it's possible, but it's not that easy. And then to embed it in R3, we don't know how to do that. So, so this is, for example, an open question already. And then obviously an open question is that like for every D, what is the optimal result? We have an upper bound D minus 1. And then also, at least we can deduce from known result about standard WL test. This is from Kai, Führer, and Irmerman, that if I fix the dimension R to the D, at least I know that I need the dimension of the test should be linear in D at least. It cannot be that, I don't know, log D WL test is complete in D. And this basically follows from the result that one can construct graphs. So if I want to fool, let's say KWL, it's enough to construct, it can be fooled by graphs that have linear number of nodes in K. And then after that, if I have these two graphs, I can embed it in RD. In which sense? So I will just map edges, all edges into the same distance. So all pairs of nodes that will have the same, that are edges will be mapped to pairs of nodes of the same distance, and non-edges into some other distance, but also the same for all non-edges. And then this geometric stuff will basically work the same as the WL test for graphs. And to embed graph in this way, you need, I think, so for example, in this way, if I have 5 nodes, well, okay, for example, if I have 3 nodes, I can embed it into a plane. So I need RD to be even, well, it's not that important, basically the same dimension as there are nodes of the graph. Yeah, so basically then I guess I have to stop, and because it's already almost 50, right? So, and then I will be happy to answer questions if there are.
Okay,
Some.
thank you, Alexander. Let us thank Alexander, please. Yeah, physically or virtually. I am stopping the recording.